When we look at the natural world, we see a staggering diversity of plants and ecosystems. But we aren't watching biology in action. We're looking at a static collection of historical success stories. We treat evolution as a finished product, the visible characteristics of a living organism. Yet the hidden engine that produced these characteristics is the mechanical process of natural selection. Observing this filtration process in real time is impossible if we only study large animals. To see the mechanics clearly, we have to scale down and look at microscopic life. Single-celled microbes divide and multiply at extreme rates. A single bacterium can become a population of millions within hours, condensing what would take millions of years for mammals into a single afternoon. Looking at this petri dish, we see a wide array of bacterial colonies. Even within a single medium, these bacteria possess distinct metabolic variations. If we change the chemical composition of this medium, we introduce a new environmental filter. The dominant bacteria might suddenly starve, while a tiny subset of the population with a compatible metabolic variation survives to consume the new feed and multiply. This rapid, microscopic filtration is the exact same mechanism responsible for macroscopic animals, stretched across agonizingly long life cycles and millions of years. To accurately map how life takes shape, we must discard the deeply ingrained myth that organisms try to adapt to their surroundings. Natural selection is a blind, passive mechanical filter. Tracing the discovery of this engine requires looking back at exactly how early biologists got the mechanism wrong. Before Darwin, the French naturalist Jean-Baptiste Lamarck proposed a hypothesis for how life forms change over time. Lamarck argued that evolution was an active pursuit, driven by the continuous use and disuse of physical organs. This diagram illustrates Lamarck's most famous example. He suggested that giraffes, repeatedly stretching their necks to forage leaves high in the canopy, acquired longer necks through physical effort. Lamarck assumed this physically acquired characteristic was then passed directly down to the next generation. The fatal flaw in this logic is biological. Physical exertion has no underlying genetic basis. An animal can build muscle or stretch its limbs over a lifetime, but without a heritable genetic foundation for those traits, there is nothing for nature to select and nothing to pass on. Biological change cannot be driven by an organism's physical effort or need. The intentional adaptation model completely fails. Charles Darwin recognized this flaw and searched for a strict mechanical driver of biological change rather than an intentional one. He found his mechanism in the work of Thomas Malthus, who studied the factual limitations of natural resources and population dynamics. This graph charts Malthus's mathematical reality. Left unchecked, any biological population grows on a steep exponential curve. But physical space and natural resources are strictly finite, forming a rigid ceiling. This collision creates a Malthusian bottleneck, forcing competition where only a fraction survive. Apply this mathematical bottleneck back to the microscopic scale. Imagine a stable environment perfectly suited to a specific dominant bacterial strain. Suddenly, a hostile shift in the environment heavily restricts the available resources. The dominant strain starves off. Meanwhile, a minor, previously insignificant variant strain happens to possess the specific biological traits required to utilize the remaining resources, allowing it to rapidly overtake the population. This redefines biological fitness. It is not physical strength. It is simply possessing the heritable genetic capacity to outcompete others for resources in a specific setting. The crucial chronological fact is that the genetic variation granting this fitness must exist before the environment changes. The environment does not create the variation. Nature does not force an organism to adapt. It acts as a passive Malthusian filter, preserving only those whose existing genetics allow them to survive the new reality. Darwin mapped the strict rules of selection, but his theory contained a massive gap. He failed to explain where the initial variations came from. He accurately observed that crucial survival traits were heritable, but he could not mechanically explain how those traits originated in the first place. In the first decade of the 20th century, the biologist Hugo de Vries set out to find the origin of biological variation. He conducted his primary biological work by studying the evening primrose plant. Through his research, de Vries introduced a radical contribution to genetics. He identified mutation as the ultimate source of new traits. The left side of this comparison charts Darwin's assumption of biological variation. He believed changes were small, incredibly slow, and highly directional. But on the right, de Vries observed single-step, large-scale genetic mutations arising suddenly in a population, a phenomenon he called saltation. The defining characteristic of these genetic mutations is that they are entirely random. They are directionless errors, completely blind to whether they help or harm the organism. De Vries' random, undirected mutations provide the raw biological material required to feed Darwin's relentless Malthusian engine. By combining the validated components of these historical theories, we arrive at the modern framework of population genetics. Step 1. De Vries' random mutations blindly generate a massive spectrum of heritable variations across a species. Step 2. Malthusian mathematics guarantee the population will over-reproduce until it crashes into the strict resource limits of its environment. Step 3. Darwinian directional selection acts as the sorting mechanism, systematically killing off unfavorable mutations and leaving behind only the survivors. When you apply this exact three-step microscopic engine across entire continents and millions of years, you get the macroscopic phenomenon of convergent evolution. Convergent evolution occurs when geographically isolated, genetically distinct lineages develop nearly identical physical forms. This side-by-side chart maps the parallel branches of placental mammals and Australian marsupials. It provides visual proof of distinct ancestral lines arriving at the exact same functional body plans. Even with entirely different starting genetic codes, when populations are subjected to the exact same environmental bottlenecks and resource limits, the environment will systematically select for identical functional traits. This leaves us with the true definition of evolutionary fitness. It is simply the end result of blind variation successfully navigating a hostile mathematical filter. The diversity of the natural world is not a story of conscious striving or physical effort. It is the spectacular, inevitable consequence of biological limits acting upon random generic errors.